This is one of the ways we pictured ourselves traveling back in time. To be able to do so, we have to move faster than the speed of light, but the special theory of relativity tells us it's impossible to accelerate an object to the speed of light, let alone exceeding it. So, those dreams of building your own time machine and using it to travel to the old good days, to watch Muhammad Ali perform his famous shuffle live, to see how the great pyramids of Giza were built, to find out if King Arthur was real, are not destined to be true. But what if I told you that traveling in time is as simple as looking deep into the sky? Think of it, light from the sun takes 8 minutes to reach us here on Earth, which means you are always looking at how the sun looks 8 minutes ago. But of course you are not here to travel 8 minutes, are you? First of all, our sun is 150 million kilometers away. That sounds like a big number, right? Trust me, on the scale of the universe, this number is not existent. Take Sirius for example, which is one of the close stars to our sun. It's more than 81 trillion kilometers away. Guess how much time light takes to travel this distance? Which means if the star ceased to exist, we wouldn't be able to tell until 8.5 years later. So, if we are looking at the 8.5 years younger version of Sirius, which on the scale of the Milky Way is considered next door, what happens if we look outside our entire galaxy? Look at Andromeda, our neighbor galaxy, and you will see how it existed 2.53 million years ago. Oh, that accelerated faster than you expected. So forget about the time machine, forget about the insignificant amount of time it would have taken you, and look into the heavens, because that's all you need to travel as much back in time as you wish, even if it's the beginning of this entire universe. Just have the courage to look 13.8 billion light years deeper into the heavens. But is it possible to look this deep? With our naked eyes, we cannot see anything beyond the Andromeda galaxy. However, with the help of
James Webb Space Telescope.
James Webb Space Telescope?
Well, it's a time machine.
Yeah,
So
basically,
The further it looks, the further those objects are
All about the
away,
amount of light you can
the further
collect when it
back
comes
in
to
time
astronomy.
you
You can
see
see farther, you can see fainter things. So everything from seeing little planets around other stars in the sky to actually seeing the very first stars turn on.
We'll also look at these worlds out there, exoplanets, that may or may not harbor
Everything we
life.
know about, everything we can see, me and you, everything on the planet, all the hundreds of billions of other galaxies, all of that only makes up about 5% of the universe. The rest of it, that other 95%, we have no idea what it is.
It had never been done before to build a big unfolding telescope in space, because we knew we needed something that was bigger than the rocket to achieve the scientific discoveries that we wanted to make. For me, building the equipment that can make a great discovery has always been like one of the most honorable things one could ever do. And to me, this James Webb Telescope is the pinnacle of what I could imagine working on in my professional life. I can't imagine anything better.
Have you ever asked yourself why light tends to appear fainter as we move farther from its source? Well, because its intensity is inversely proportional to the square of the distance of the source of light. In simple words, as light is traveling towards us, it's spreading out and covering a large area, and so the number of photons that would end up in your eye's retina are very little, causing the image to appear faint, or if the distance is enough not to be seen at all. This is basically the reason why you cannot recognize your friend from a distance, unless you are the blue-eyed woman of Yamama. In order to bypass this limitation, we use telescopes, which can help us collect photons and magnify light from distant objects. You can think of it as a bucket for collecting light. The history of the telescope is gonna take us as far back as 1608 in the Netherlands, when a patent was submitted by Hans Lippershey, an eyeglass maker. He did not receive his patent, but news of the new invention spread across Europe. As you can imagine, such a device can be a game changer in words. The design of this refracting telescope consisted of a convex objective lens and a concave eyepiece to bend rays of light and magnify an image. The following year, Galileo Galilei improved on the design and became the first person to record observations of the sky made with the help of the telescope. Craters of the moon, Saturn, 4 moons revolving around Jupiter. The sun was the center of the universe, not the earth. There are way more stars than what our eyes can see. These are some of the many observations made possible by Galileo's primitive telescope. But even so, the future didn't look so bright for the refracting telescope, because it suffered from something called chromatic aberration, which is the telescope's inability to focus different wavelengths, aka colors, on the same point. To mitigate this effect, scientists had to made longer telescopes, but it wasn't a practical thing for the long run. It was impossible to keep the lenses properly aligned at such long lengths, and because we faced this problem before we even had started scratching the surface of the cosmos, we had to improvise. The solution was replacing lenses with mirrors. Now we will reflect rays of light to magnify an image instead of bending them, and just like that, the reflecting telescope, the one that would later become the most commonly used telescope among astrologers, came to existence. It was invented in the 17th century by Isaac Newton, after numerous experiments of different methods and polishing techniques. At first, this type of telescope was hard to make. The mirrors were hard to polish to the proper shape, so we needed another 50 years to improve on Newton's design and change the mirror's spherical shape with a parabolic one, which is better at focusing all of the light at one point and thus provide crisper images. And since making bigger mirrors was more practical than making bigger lenses, we kept making the telescopes grow in size, complexity, and of course power, until we made the Hooker telescope in 1917. It was the largest aperture telescope from its completion to 1949, the one Edwin Hubble used to make observations that produced two fundamental results, which have changed our view of the universe. Up until then, our perception of the cosmos fell within the bounds of the Milky Way. We had no observable evidence, only speculations about the existence of other galaxies. Then Edwin Hubble came and reimagined our place in the universe, which is not only home to millions of other galaxies, but the universe itself is expanding. Extrapolating all the way back in time, we concluded that the universe as we know it today was an infinitely hot and dense point that's been stretching and expanding for the last 13.8 billion years. A beam of light can travel millions of light years in space holding a crystal clear image of an object, but once it penetrates the fluid chaotic soap of gas and dust that make up the Earth's atmosphere, it loses a huge amount of details. To mitigate this effect, scientists had to place their telescopes as far above the haze of the atmosphere as possible. They also used deformable mirrors and other image processing techniques to refocus the blurred images. This had minimized the effect but not utterly diminished it. So, our desire to understand how planets and galaxies form, to capture the billions stars and galaxies, to learn more about black holes and maybe spot one of them, to unravel the dark energy mystery, to pinpoint how old is the universe, wasn't meant to be fulfilled from Earth.
6, 5, 4, 3.
On April 24, 1990, Hubble Space Telescope, the first major optical telescope to be placed in space, made it to orbit. It featured a 2.4 meters mirror, which is too small compared to the ground-based telescopes, but the spacecraft's position above the atmosphere gives it incredible clarity. For scientists, it was a one-in-a-lifetime moment that had finally taken place, after numerous delays and $1.5 billion spent on development and launch. But nothing matters. Now that we have given Hubble the unobstructed view of the universe, all the questions that's been haunting us for so long are now about to be answered. We are ready to whatever surprises the universe may throw at us.
Yesterday, NASA admitted that its multi-billion-dollar eye in the sky has developed blurry vision.
No, that wasn't the surprise we were hoping for. The Hubble's main mirror had a minute defect, a spherical aberration caused by a manufacturing error. A 1/50th the thickness of a human hair aberration made the images look like this, which rendered the whole telescope useless scientifically. 3 years is the amount of time it took us to fix the error and started getting sharp images right off the telescope's digital camera. We were lucky because the spacecraft wasn't far away from Earth, and it was designed to be served by astronauts, and since replacing the mirrors was something impractical, NASA decided to correct Hubble's astigmatism, the same way a nearsighted person gets corrected with glasses. In December 1993, the first new images from Hubble reached us here on Earth, and this was our reaction when we first saw them. Since its mission began in 1990, Hubble has made more than 1.3 million observations, helped pin down the age of the universe now known to be 13.8 billion years, roughly 3 times the age of Earth, helped determine the expansion of the universe's acceleration, apparently driven by a mysterious force known as dark energy. We still don't know what dark energy is, even though it makes up most of the universe. Hubble also discovered that every major galaxy is anchored by a black hole at the center, created a 3D map of dark matter, which is like dark energy. We know a lot about what it is not, and nothing about what it actually is. The spacecraft was able to make all of this happen even though it sees only this very little portion of the light, which is mostly visible light. Am I confusing you? Well, listen. The light you and I can see is a part of a range of radiation known as the electromagnetic spectrum. The size of the wavelengths is what determines how they look and the amount of energy they contain. Light's wavelength and energy are inversely proportional. If the wavelength is short, the energy is high, and vice versa. Most of the universe is invisible to us because our eyes are limited to a very small range of the electromagnetic spectrum. But fortunately, our technology is not. We are able to make different telescopes targeting different wavelengths of the electromagnetic spectrum. But why? Why do we need to see the universe through different wavelengths? Why don't we stick to the ones our eyes can see? First, because the universe is full of objects that produce different range of radiations. The most energetic objects in space, such as black holes, emit high energy light with short wavelengths. Planets, on the other hand, which are too cold to produce visible light, radiate brightly in infrared. You as well, your cup of tea. Everything in the universe emits infrared, unless its temperature is 0 Kelvin. Second, unlike the long wavelengths of infrared, the short wavelengths of visible light are prone to bumping into particles in their way to us. So looking at the beginning of the universe through visible light is not a practical thing. These are images for the same thing in both visible light and infrared. As you can see, in infrared more stars are popping up because it's allowing us to peer inside the clouds of dust. But even if somehow the visible light manages to escape every obstacle in its way, if the distance is billions of light years, by the time the beam of light reaches us, it's no longer visible because the universe is expanding and it's causing light to stretch to a longer and redder wavelength. So light is seen as shifted towards the red part of the spectrum. And of course, the farther the light source, the greater the redshift. This is Spitzer, one of NASA's great four observatories, dedicated to looking the universe in infrared. During its mission that lasted for 17 years, orbiting the Sun on almost the same path as Earth, in the Earth-trailing orbit, benefiting from a cooler environment. Yes, low temperature is viral when it comes to infrared telescopes, because at the end of the day, infrared is what we experience as heat. So the observatory's instruments must be extremely cold, so that their inherent heat doesn't interfere with the measurements. And with only 0.85 meter mirror, Spitzer was able to produce the first ever weather map of an exoplanet. It also gave us an unprecedented view into regions where stars are born. Then it discovered 7 Earth-sized planets orbiting a star known as TRAPPIST-1. At least 3 of the planets sit in the habitable zone around the star, where temperature might be right to support liquid water on a planet's surface. Not to mention using it to study the evolution of galaxies from the ancient universe to today. Scientists also compiled more than 2 million Spitzer images, collected over 10 years, to create one of the most extensive maps of the Milky Way galaxy ever made. Not to dismiss its contribution in studying GNZ 11. A galaxy 31.96 billion light-years away. It was observed as existed 13.4 billion years ago, only 400 million years after the Big Bang. Yes, it's 31.96 billion light-years away, but light took only 13.4 billion years to reach us. How? First of all, I want you to put what I mentioned at the start of this video about looking deep into space to see the beginning of the universe aside, because the truth is, looking 13.8 billion light-years deeper into space wouldn't make you see the beginning of this universe. Look, light we receive from GNZ 11 was emitted when we were only 2.6 billion light-years away from each other. As the light tried to reach us, the expansion of the universe kept moving us away from it. So light would need 13.4 billion years to finally catch up. During this 13.4 billion years, the expansion of the universe has turned the 2.6 billion light-years distance into 31.96 billion light-years. And also light from the galaxy is shifted to a longer and redder wavelength. I hope that explains why it's a high redshift galaxy and why it's holding the record for the farthest galaxy we are able to observe since 2016. Apparently this record will stand until it's broken by the largest, most complex and powerful space telescope ever built. Just like Spitzer, the James Webb Space Telescope is also optimized for infrared wavelengths, with greatly improved sensitivity and longer wavelengths coverage. This will allow him to peer inside the dense clouds of dust where stars are born, and also look back in time to find the first galaxies that formed few million years after the Big Bang, in a period known as the Cosmic Dawn. This unprecedented scientific power is a result of both the size of the primary mirror and the extreme sensitivity and precision of its 4 scientific instruments, making him able to detect things that are 10 million times as as faint as the faintest star visible without a telescope. In other words, if you light a candle here on Earth, you can see it from his orbit. Webb has a much larger mirror than Hubble, giving it more light gathering power. However, building a mirror this large is challenging even for the ground use, let alone launching it into space, which is something we've never done before. So we decided to build the mirrors in segments on a structure which can fold up so that it can fit into a rocket. Unlike Hubble that has a single 2.4 meters mirror, Webb's primary mirror is 6.5 meters across, involving 18 gold-coated hexagonal sections that fit together. These segments are made from beryllium, which is light and strong, and most importantly, it can hold its shape perfectly across a range of temperatures, and this time to avoid any flaws in the mirror. Each segment has 6 actuators that can move it into proper alignment, or maybe change its shape to ensure a proper curve with 10 nanometers precision. The spacecraft has infrared instruments with both near and long wavelength coverage. The near-infrared instruments will work at about 39 Kelvin, achieved possibly thanks to a 5-layer tennis court-sized sun shield, protecting it from light and heat sources such as the sun, earth and moon. These 5 layers are made out of a material called kapton, which has a high heat resistance and remains stable across a wide range of temperatures. And because kapton is transparent, each layer is coated with aluminium to reflect heat back into space. Just like the mirror, the sun shield has to be folded up to fit within the fairing of the launch rocket. It's like a parachute, no matter how much you test it. It always depends on the last time you fold it. And by the way, each layer is as thin as a human hair. So imagine crumpling a tennis court-sized piece of paper, then having it to uncrumble itself in space when there is no gravity. To operate properly, the mid-infrared instruments has to be at a temperature of 6.7 Kelvin. This very low temperature cannot be achieved passively. So James Webb carries a cryo-cooler dedicated to cool Meares detectors. One of the cryo-cooler's most challenging requirements is low vibration to avoid shaking, which would compromise the quality of the images. The perfect location for the sun shield to block out the light and heat of the sun, earth and moon is this place right here. The sun and the earth, just like any two huge masses, have 5 points called the Lagrange points, where their gravitational forces cancel each other out, and small objects can stay in the same position relative to both of them. In this point, GWST can orbit the sun in synchrony with the earth, and because L2 is not a perfectly stable point, regular course and altitude correction has to be made occasionally. That's why the giant super-sensitive instruments had to be made as lightweight as possible, to consume less fuel and prolong the observatory's lifespan. This point lies approximately 1.5 million kilometers away. The option of repair by astronauts is not available this time, so if anything goes wrong, that means we have spent $10 billion and 13 years of hard work to beat a dead horse. On December 25, 2021, GWST was placed on the Ariane 5 launch vehicle, which provided thrust for 26 minutes after liftoff from French Guiana. Then Webb separated from the launch vehicle and deployed the solar array immediately afterward. 2 hours after launch, it deployed its high-gain antenna. Then the first trajectory correction maneuver by a small rocket aboard Webb took place. Shortly after, we executed the second trajectory correction maneuver. The most complicated deployment sequence humanity ever done started taking place once we lowered the sun shield pallet and separated the Webb's path from the primary mirror and instruments, the sun shield membranes and pin, and the telescoping sun shield mid-bombs extended, pulling the 5 sun shield layers with them. Once the sun shield successfully deployed, we were able to release the first sighs of relief, because it took the lion's share when it comes to complications. But it's not over yet. Time to set up the optics.
And we have a fully deployed JWST observatory.
The bright star in front of your screen right now is the one used as a focus point for the alignment of the hexagonal mirrors. But as you can see, galaxies and stars showed up out of the blue, confirming that Webb's optics and near-cam sensitivity is in a whole other level. In fact, Webb's optical system has exceeded our expectations. Now the only thing standing between us and the new astonishing scientific discoveries is the time the instruments need to reach the optimal temperature we talked about before. But once that happens, we will be able to reveal new wonders in our solar system, our galaxy and beyond, such as understanding how galaxies evolved from their humble beginning to the large organized structure we see today, how clouds of gas and dust collapse to form stars, and of course investigating the potential of life in other planetary systems.